Tonight, we're going to talk about something that, according to most of what we understand about telescope physics, should not have been possible. And when I say it shouldn't have been possible, I don't mean it was difficult. I don't mean it required clever engineering. I mean the combination of factors working against this observation was so severe that for decades, no instrument humanity ever built could overcome them. The James Webb Space Telescope has now observed Pluto in the mid-infrared for the first time in history. And what it found there rewrites what we thought we knew about how that world works. Let's establish the problem. Pluto sits roughly 40 times farther from the Sun than Earth does. That distance alone is staggering. Light from the Sun takes about 8 minutes to reach us. It takes over 5 hours to reach Pluto. The telescope observing Pluto isn't looking across town. It's looking across a distance so vast that the signals arriving from that world are almost indistinguishable from silence. And Pluto is small. Its diameter is only about 2,400 kilometers. That's smaller than our own moon. A world that size, at that distance, appears in the sky as something not much larger than a point of light. Even through the finest telescopes ever built before JWST, Pluto was barely a smear of pixels. Then there's temperature. Pluto's surface drops to around minus 380 degrees Fahrenheit. At that temperature, objects emit almost no thermal radiation. The faint infrared glow Pluto does produce sits in a wavelength range, the mid-infrared, between roughly 5 and 27 micrometers, that no previous space telescope had the sensitivity to measure from this world. The signal is real. It was always there, but it was buried so deep beneath the noise floor of every instrument we had that it simply could not be reached. Not by Hubble, not by Spitzer, not by anything. And there's one more problem. Pluto has a large moon called Charon, orbiting so close that their thermal signals overlap when viewed from Earth's distance. For years, researchers couldn't separate what was coming from Pluto and what was coming from Charon. Without that separation, you can't study either one properly. The whole system blurred together into a single ambiguous signal. The science that depended on untangling it simply had to wait. JWST didn't just overcome those obstacles, it resolved all of them at once, and what came back in the data was remarkable. For the first time, scientists measured Pluto's atmospheric haze, emitting a real thermal signature, something that had been predicted by models in 2017, but never confirmed. That confirmation turned out to mean something profound. Pluto's climate is controlled by its haze, in a way that has no equivalent anywhere else in the solar system. JWST also revealed unexpected chemical compounds on Charon's surface and provided new detail on how temperature varies across both worlds as they rotate. If you want to understand why any of that matters, what Pluto actually is, why seeing it required building an entirely new kind of telescope, what the discoveries mean for our understanding of worlds at the outer edge of the solar system, stay with us. And if exploring the deep physics of places like this is the kind of thing you find yourself coming back to, take a second to like this video or subscribe. It's a small thing, but it helps reach people who are curious about the same questions. Now, let's start at the beginning, with the small, frozen, impossibly distant world at the center of all of this. Pluto sits at the edge of our solar system, in a region so remote and so cold that most people, when they picture it, imagine something simple, a grey ball of ice drifting alone through the dark. That picture is wrong. It was always wrong. And part of what makes the JWST story so interesting is that the world JWST observed was already far stranger than our textbook suggested, before a single new measurement was taken. Start with the basics. Pluto was discovered in 1930 by a 24-year-old astronomer named Clyde Tombaugh, working at the Lowell Observatory in Arizona. For 76 years, it held the title of the 9th planet. Then, in 2006, the International Astronomical Union voted to reclassify it. Pluto was demoted to dwarf planet status, and the public reaction was immediate. People felt something. They felt that Pluto had been wronged. But here's what most people don't realize about that reclassification. It wasn't a punishment. It wasn't a political decision. It was a recognition of what Pluto actually is. By the early 2000s, astronomers were finding other objects in the outer solar system, large, icy bodies in the same neighborhood as Pluto, some of them nearly as big. Eris, discovered in 2005, was actually thought to be slightly more massive than Pluto at the time. The question was simple. Either the solar system had dozens of planets, or Pluto wasn't a planet. The IAU chose the definition that fit the science. Pluto hadn't changed. Our understanding of its neighborhood had. So what is it exactly? Pluto is a dwarf planet orbiting in the Kuiper Belt, a vast ring of icy bodies that extends beyond Neptune. Its diameter is about 2,400 kilometers. That is smaller than Earth's moon, which measures about 3,474 kilometers across. Think about that for a moment. Our moon is a companion body, a satellite, something we have always treated as secondary, and yet Pluto is physically smaller. If you place Pluto on top of the continental United States, it would not reach from coast to coast. It is not a large object. It is remarkably small for something that held planetary status for 3/4 of a century. Its surface is dominated by ices, not the water ice we're most familiar with. The primary ice on Pluto's surface is nitrogen ice, the same nitrogen that makes up most of our own atmosphere, frozen solid at Pluto's extreme temperatures. Methane ice and carbon dioxide ice also cover large portions of the surface. These are not exotic materials in the universe, but their existence as surface ices tells you something immediate about how cold Pluto is. Nitrogen freezes at around -346 degrees Fahrenheit. Surface temperatures on Pluto drop to approximately -380 degrees Fahrenheit. That is close to the coldest possible temperature matter can reach. The difference between -380 degrees and absolute zero is smaller than the difference between a warm afternoon and a cold winter night on Earth. Pluto's orbit is nothing like Earth's. Earth travels around the Sun in a path that is nearly circular. Pluto's orbit is highly elliptical. At its closest approach to the Sun, Pluto comes within about 30 astronomical units, 30 times the Earth-Sun distance. At its farthest, it reaches nearly 49 astronomical units out. One complete orbit takes 248 years. That means Pluto has completed less than one full orbit around the Sun since it was discovered. It hasn't even made it back to where Tombaugh first spotted it. The variation in distance matters enormously for the planet's climate. When Pluto is closer to the Sun, its surface ices begin to sublimate, converting directly from solid to gas, and a thin atmosphere temporarily forms. As it moves outward, that atmosphere collapses back onto the surface. The planet's climate is driven by a 248-year orbital cycle that no human civilization has ever watched from beginning to end. Now, Charon. Most people think of Charon as Pluto's moon. That framing is technically correct, but practically misleading. Charon is about 750 miles wide, roughly 1,200 kilometers in diameter. That is enormous relative to the body it orbits. Charon is more than half the size of Pluto. Compare that to our own moon, which is about a quarter of Earth's diameter. The mass ratio between Pluto and Charon is so close that the gravitational center of their system, the barycenter, the point around which both objects orbit, sits outside Pluto's surface entirely. It is a point in empty space between the two bodies. Both Pluto and Charon orbit around that empty point. That is not a planet and its moon. That is a binary system. No other pair of bodies in the solar system has this relationship quite like Pluto and Charon do. They are tidally locked to each other. Pluto always shows the same face to Charon. Charon always shows the same face to Pluto. They rotate together like two objects attached by an invisible bar, spinning slowly every 6.4 Earth days. From Pluto's surface, Charon would hang motionless in the sky. It would never rise or set. It would just sit there, enormous, filling a wide arc of the horizon. Charon itself turned out to be its own kind of strange. Its surface is dominated by water ice and ammonia-based compounds. It has dark reddish polar regions that most planetary scientists believe are the result of methane escaping from Pluto's atmosphere and being chemically altered on Charon's surface by ultraviolet radiation from the Sun. The two worlds are interacting. Material is moving between them. That is not typical planetary science. That is something weirder. This is what Pluto looked like before JWST arrived. Not a simple grey ball. A binary world with a climate cycle 248 years long, surfaces covered in exotic ices, temperatures near absolute zero, and an intimate gravitational partnership with a moon so large it barely qualifies as a moon. Pluto was already more complicated than we thought before JWST ever turned its mirrors toward it, and the complications were only just beginning. Here's the problem with looking at Pluto through a telescope, and it's not a small problem. It's actually 3 problems stacked on top of each other, and each one alone would be enough to make most telescopes give up entirely. Together, they create something close to an observational impossibility. To understand why JWST's achievement matters, you need to understand exactly what it was working against. Start with distance. Pluto sits roughly 6 trillion meters from Earth. That number is almost meaningless on its own, so let's put it another way. Pluto is about 40 times further from the Sun than we are. Light travels at 186,000 miles per second. It takes sunlight about 8 minutes to reach Earth. That same light takes over 5 hours to reach Pluto. When you point a telescope at Pluto, you are not looking at something nearby. You are looking at an object so remote that the signals it sends back take hours to cross the space between you. At that distance, Pluto's apparent size in the sky is extraordinarily small. Its angular diameter, the angle it subtends when viewed from Earth, is roughly 0.1 arcseconds. Think about what that means. A full moon spans about 1,800 arcseconds across. Pluto spans 1/10 of one of those. It is, for all practical purposes, a point of light. Not a disk, not a surface, a point. Even the finest telescope on Earth sees nothing there but a faint dot against the dark. That distance also means Pluto's light is phenomenally faint. The Sun's light reaches Pluto at about 1/1600th the intensity it reaches Earth. Whatever sunlight bounces back toward us from Pluto's surface has already made the 5-hour journey out, then faces the same 5-hour journey back. By the time it arrives at a telescope mirror, it has been diluted across an enormous sphere of space. The signal is not just weak, it is almost imperceptibly weak, and visible light is the easy part. Here's where the second problem makes everything worse. At -380 degrees Fahrenheit, Pluto is extraordinarily cold. Cold objects emit thermal radiation, but the wavelength of that radiation depends on temperature. The hotter an object, the shorter the wavelengths it primarily emits. The Sun, burning at roughly 10,000 degrees Fahrenheit at its surface, peaks in visible light. Pluto, at nearly 400 degrees below 0 Fahrenheit, emits thermal radiation in the mid-infrared, at wavelengths between roughly 15 and 25 micrometers. These are not wavelengths that human eyes detect. They are not wavelengths that optical telescopes like Hubble were built to study. They are long, slow waves of heat radiation, and Pluto produces very little of them. The total mid-infrared thermal emission coming off Pluto is extraordinarily faint. Not faint the way a distant star is faint. Faint the way a tiny frozen rock on the other side of the solar system is faint, which is to say barely distinguishable from nothing. Detecting thermal emission at those wavelengths requires a specialized infrared instrument operating at extremely low temperatures. The instrument itself has to be cold, because any warmth in the detector produces its own infrared glow that contaminates the measurements. You cannot build a room temperature instrument and point it at Pluto expecting to detect mid-infrared photons from its atmosphere. The thermal noise from the instrument will simply overwhelm the signal. This is a fundamental physics constraint. It cannot be engineered away cheaply. It requires extraordinary design, And even then, it almost doesn't work. Now add the third problem. Even if you have a cold enough instrument and a large enough mirror to gather light from 6 trillion meters away, you still face the signal-to-noise challenge. Space is not silent. The background of the sky at mid-infrared wavelengths contains its own glow from interplanetary dust, from distant warm objects, from the telescope structure itself, from cosmic sources scattered throughout the field of view. Pulling a genuine detection of Pluto's thermal haze out of that background requires not just sensitivity, but extreme sensitivity. You need an instrument capable of detecting a thermal signal that is almost buried in the noise floor of the observation itself. Prior to JWST, no instrument came close to that threshold for an object at Pluto's distance and temperature. The numbers simply didn't work. Pluto's thermal emission was buried under everything else. Think about what this means in practice. Pluto is smaller than Earth's moon. It is 40 times farther from the Sun than Earth. Its surface is nearly 400 degrees below 0 Fahrenheit. It emits thermal radiation at wavelengths that require specialized instruments operating near absolute zero to detect. And the total amount of that thermal radiation arriving at a telescope near Earth is so small that it barely registers above the noise of space itself. Each one of these facts would be a challenge. Together, they form a wall. The cumulative effect of these three obstacles had historically placed Pluto beyond the reach of conventional infrared astronomy. Instruments designed for other observational purposes simply lacked the necessary specifications to isolate Pluto's thermal signature from the cosmic noise surrounding it. The problem was not one of theoretical impossibility, but of practical limitations. No existing observatory could simultaneously overcome Pluto's extreme distance, minuscule apparent size, profound cold, and weak thermal emission. Previous space missions had provided remarkable images of Pluto's surface, but these relied on reflected sunlight captured during the New Horizons Flyby's close approach. Sustained thermal observation from Earth orbit, continuously gathering infrared photons to characterize Pluto's atmosphere over extended observation periods, had remained beyond reach. The combination of constraints formed a barrier that appeared insurmountable without a fundamentally different technological approach. And there is still a fourth complication that makes everything harder. Pluto is not alone. Charon orbits it at a distance of about 19,600 kilometers. That might sound like a comfortable separation, but from Earth, the angular distance between Pluto and Charon is only about 0.9 arcseconds at maximum. Most of the time they are closer than that in the sky. An instrument trying to measure Pluto's thermal emission will almost inevitably pick up Charon's thermal emission at the same time, because their signals overlap in the telescope's view. You cannot simply point at Pluto and measure Pluto. You are unavoidably measuring a combined signal from two worlds at once. And if you cannot separate them, you cannot study either one individually. You cannot determine what Pluto's atmosphere is doing thermally versus what Charon's surface is doing. You cannot confirm whether the haze emission predicted by climate models is actually there, because you cannot isolate Pluto's spectral contribution from the noise introduced by its large moon orbiting nearby. This is not a problem that patience or clever data processing can fully solve with an insufficient instrument. The spatial resolution required to cleanly separate these two thermal sources at mid-infrared wavelengths demands a mirror large enough and an instrument sensitive enough to distinguish between objects separated by less than an arcsecond in the sky. That is a demanding technical requirement, even for a world-class observatory. The Hubble Space Telescope spent decades unable to cleanly separate Pluto's signal from Charon's, not because of poor design, but because of basic physics that no amount of engineering could work around. Not until JWST. For decades before JWST launched, astronomers weren't ignoring Pluto. They were working on it constantly, pushing every available instrument to its limit, trying to extract useful science from one of the most frustrating observational targets in the solar system. They made real progress. They also kept running into the same wall over and over again, in different forms. The wall was always the same thing. The technology didn't exist yet. Not because no one was trying to build it, because what Pluto required was genuinely beyond what any instrument of those decades could deliver. Let's start with Hubble. The Hubble Space Telescope gave us our best pre-New Horizons view of Pluto. By the standards of ground-based observation, Hubble's images were remarkable. They resolved Pluto as a small, blurry disk rather than a simple point of light. Scientists could see broad regions of light and dark across its surface. They could map rough albedo features, patches of brighter or darker material. They could track how those features shifted as Pluto rotated. That was genuinely useful. It confirmed that Pluto's surface wasn't uniform. It had structure, complexity, variation. But here's what Hubble couldn't do. It couldn't tell you what those bright and dark regions were actually made of at any useful level of thermal detail. It couldn't measure how hot or cold those regions were. It had no meaningful mid-infrared capability for an object this faint and this distant. Hubble's strength was optical and ultraviolet astronomy. Pluto's thermal story lives in the mid-infrared. Those two things don't overlap. Ground-based spectroscopy filled in some of the chemical picture. By studying how Pluto absorbed different wavelengths of reflected sunlight, astronomers identified nitrogen ice, methane ice, and carbon monoxide ice on its surface. That was significant. It told scientists that Pluto had a complex, icy chemistry and a thin atmosphere that exchanged material with the surface. They could track seasonal changes in the methane and nitrogen absorption features as Pluto moved through its long orbit. They built models of the surface composition. They understood, broadly, what was there. What they couldn't determine was the thermal behavior of any of it, the temperatures of individual surface regions, the rate at which different ices were sublimating and redepositing, the energy balance between the surface and the atmosphere. None of that was accessible. The Spitzer Space Telescope was designed precisely to study the infrared universe. Launched in 2003, it was the most capable infrared space telescope of its era, and Pluto defeated it. Spitzer could observe in the mid-infrared, wavelengths out to about 160 micrometers, but its mirror was only 85 centimeters across. That's a small collecting area. The amount of thermal radiation arriving from Pluto at Spitzer's distance was so faint that the instrument simply couldn't pull it out of the noise with any confidence. Think about what that means. The most capable infrared space telescope humans had ever built couldn't reliably detect Pluto's heat signature. That's not a marginal shortfall. That's a fundamental gap between what the science required and what any existing technology could provide. Here's what makes this genuinely frustrating. Scientists knew exactly what they were looking for. They had theoretical models predicting how Pluto's atmosphere should behave at mid-infrared wavelengths. They had predictions, specific, detailed, testable predictions about what the thermal emission from Pluto's atmospheric haze should look like. Those predictions existed years before JWST launched. The science was there, the questions were well formed, but there was no instrument on Earth or in orbit around it that could go test whether those predictions were correct. Decades of theoretical work, staring at a question that could be answered in principle but not in practice. The mid-infrared range from about 5 to 27 micrometers had simply never been explored for the Pluto-Charon system in any meaningful way. That entire spectral window, the one where Pluto's thermal emission lives, where its atmospheric haze was predicted to glow, where the thermal properties of its surface ices would finally become legible, was a blank. Not a partially filled-in blank, not a rough sketch, a complete blank. No measurements, no data, no constraints. For a world that had been known to astronomers since 1930, that's a remarkable gap. It wasn't neglect, it was the physics of what mid-infrared observation requires, combined with the reality of what every telescope built before JWST was capable of delivering. There were other instruments that contributed pieces of the puzzle. Ground-based observatories with adaptive optic systems, large mirrors, and advanced spectrographs, added to the spectroscopic picture over the years. The Herschel Space Observatory, operating at far infrared and sub-millimeter wavelengths, made some detections of the Pluto-Charon system's thermal emission at very long wavelengths, far beyond the mid-infrared range. Those measurements provided rough constraints on the total energy budget of the system. They were useful, but they couldn't resolve Pluto from Charon, couldn't access the mid-infrared range, and couldn't provide the spectral detail needed to actually characterize what was physically happening in Pluto's atmosphere. Astronomers were working at the edges of what was possible, gathering every fragment of information they could reach, while the central question remained untouched. By the early 2010s, the situation was clear. Ground-based telescopes and existing space observatories had taken the study of Pluto as far as they could carry it. The surface composition was broadly mapped. The atmosphere was known to exist and to exchange material with the surface. The orbital and physical parameters were well measured. And the thermal story, the mid-infrared picture of how energy actually moved through this world, was completely inaccessible. One mission was already in flight by then, aimed directly at the problem from the only angle that had ever worked. Get close enough that distance stops mattering. The only way anyone had ever gotten a real close look at Pluto was to physically go there, and that mission gave us something extraordinary, and also revealed how much we were still missing. In July 2015, after travelling for 9.5 years across nearly 3 billion miles of empty space, the New Horizons spacecraft reached Pluto. That journey alone is worth pausing on. 9.5 years. The spacecraft launched when George W. Bush was still in his first term as president. It crossed the orbit of Jupiter. It flew through the outer solar system in complete silence, receiving occasional signals from Earth, executing its programming, waiting. By the time it arrived, the scientists who built it had spent nearly a decade wondering what they would find. What they found was not what anyone expected. Before New Horizons, most models of Pluto assumed a relatively simple world. It was small, it was cold, it sat so far from the sun that not much could be happening on its surface. The assumption was that Pluto would look something like a battered, frozen rock, cratered, geologically dead, preserved in the deep freeze of the outer solar system for billions of years. Those assumptions turned out to be wrong in almost every meaningful way. The first images showing real surface detail came back in the days before closest approach. Scientists gathered around screens and watched as Pluto resolved from a blurry point into something with structure. There was a massive bright region near the equator, shaped unmistakably like a heart. That feature was named Tombaugh Regio after Clyde Tombaugh, the astronomer who discovered Pluto in 1930. It is enormous. The heart spans roughly 1,600 kilometers across the surface. The left lobe of the heart, a vast plain now called Sputnik Planitia, turned out to be covered in smooth, relatively young nitrogen ice. Young in geological terms means hundreds of millions of years old rather than billions. There were almost no impact craters on this plain. That absence meant the surface was being active, very reshaped somehow, even at the edge of the solar system. Then there were the mountains. Along the western edge of Tombaugh Regio, water ice mountains rose to heights of roughly 300-500 meters, comparable to the Rocky Mountains on Earth. Water ice at Pluto's surface temperatures behaves like rock. It is rigid enough to support that kind of vertical relief. The mountains appeared geologically young as well, which deepened the mystery. What was driving this geological activity on a world this small, this far from the sun, with no large moon to provide tidal heating the way Io's volcanism is driven by Jupiter? Nobody had a clean answer. New Horizons had raised the question before the data was even fully downloaded. The surface turned out to be enormously varied. Dark reddish terrain near the equator contrasted with bright icy plains. There were bladed ridges of methane ice at high altitudes, strange pitted landscapes, regions of crumpled, broken terrain that looked like it had been tectonically active at some point in Pluto's history. The diversity of surface environments on something smaller than Earth's moon was genuinely shocking to the science team. Pluto was not a simple frozen rock. It was a complex world with a geological and chemical history that would take years to begin unpacking. Then came the haze. When New Horizons looked back toward the Sun after closest approach, with Pluto as a backlit crescent in the frame, the cameras detected something in the atmosphere that stopped scientists cold. There was a haze, not a thin wisp of gas at low altitude, a multi-layered structured haze extending more than 300 kilometers above the surface. It had a bluish tint in the images, caused by tiny organic particles scattering light in a specific way. Before the flyby, models had predicted that Pluto might have some atmospheric haze, but nothing approaching this altitude or this complexity. The haze was layered, with at least a dozen distinct strata visible. It was one of the mission's most arresting images, and one of its most scientifically important discoveries. The haze forms when ultraviolet radiation from the Sun breaks apart simple molecules in Pluto's thin atmosphere, primarily nitrogen and methane, and those broken fragments recombine into more complex organic compounds. These compounds eventually condense into tiny particles and form the layers of haze that New Horizons photographed. The process is similar to what happens in the atmosphere of Titan, Saturn's largest moon, though at much lower temperatures and pressures. The similarity to Titan caught scientists' attention immediately. But here is where New Horizons hit its fundamental limit. The spacecraft's instruments covered ultraviolet wavelengths, visible light, and near-infrared wavelengths out to about 2.5 micrometers. That range told scientists a great deal about surface composition, surface albedo, the basic structure of the haze in reflected and scattered light. What it could not do was measure thermal emission. It could not tell scientists how warm or cold the haze particles were. It could not reveal how the haze was interacting with Pluto's energy budget, whether it was warming the atmosphere, cooling it, or doing both at different altitudes. It could not measure how surface temperatures varied across Tombor Regio versus Cthulhu, Macula versus the mountain ranges near the Terminator. The thermal story of Pluto, the story that would explain how its climate actually works, sits in the mid-infrared range, from roughly 5 to 27 micrometers. New Horizons never looked there, and New Horizons could not try again. That is the hard constraint of a flyby mission. The spacecraft arrived, gathered data furiously for a few hours, then sailed past Pluto on a trajectory that carried it out into the Kuiper Belt and eventually toward interstellar space. It will never return to Pluto. The images and spectra it collected represent a single snapshot in time, at a single set of wavelengths, of a world that was clearly changing and clearly more complex than anyone had realized. The questions it raised about the haze, what it does thermally, how it controls the climate, how it varies with the seasons of a 248-year orbit, remained completely open when New Horizons fell silent on that topic. But New Horizons had passed Pluto in a matter of hours and could never go back. The lengths it couldn't see, the mid-infrared range that holds the thermal story of a world, remained completely unexplored. The James Webb Space Telescope launched on Christmas Day 2021, and, for the first several months of its operation, spent its time looking at things on the complete opposite end of the cosmic scale from Pluto. Ancient galaxies, newborn star systems, the atmosphere of exoplanets orbiting distant suns. That wasn't an accident. JWST was built for the deep universe. The science case that justified its cost, somewhere north of $10 billion and decades of engineering, was primarily about looking as far back in time as physically possible. The earliest galaxies, the first light after the Big Bang, structures that formed when the universe was only a few 100 million years old. Pluto was not part of that conversation. Pluto is practically next door. But here's what you need to understand about JWST. The capabilities that make it extraordinary for studying ancient galaxies turn out to be exactly the capabilities that Pluto had been waiting for. That overlap is not a coincidence. But the degree to which JWST unlocked Pluto's secrets surprised even the researchers who used it to do so. Start with the mirror. JWST's primary mirror is 6.5 meters across. Hubble's mirror is 2.4 meters. That difference in size translates directly into light-gathering power. The area of a mirror scales with the square of its diameter. That means JWST collects roughly 7 times more light than Hubble. More light means fainter objects become detectable. It means signals that were previously buried in noise become measurable. For something as faint as Pluto's thermal emission, that difference is not marginal. It's the difference between seeing something and seeing nothing at all. The mirror is also made from beryllium, coated in gold. Gold reflects infrared light exceptionally well. This is not incidental to the design. JWST is fundamentally an infrared observatory, where Hubble sees primarily in visible and ultraviolet wavelengths. With some near-infrared capability, JWST operates across a range from about 0.6 to 27 micrometers. That upper end, the mid-infrared, is territory that no previous space telescope had explored with anything like JWST's sensitivity for cold, distant solar system objects. That spectral range matters enormously. Objects emit thermal radiation at wavelengths that depend on their temperature. Hot things, like stars, emit most of their energy in visible or ultraviolet light. Cold things emit in the infrared. Pluto, at nearly minus 380 degrees Fahrenheit, emits almost nothing in visible light. Its thermal signal lives deep in the mid-infrared. Previous telescopes were essentially blind to it, not because of poor design, but because they weren't designed to look there with that kind of sensitivity. JWST was. Now think about what that cold detection requires. If JWST is trying to measure heat signatures from objects at minus 380 degrees Fahrenheit, the telescope itself has to be colder than that. Any warmth in the telescope's optics or detectors produces its own infrared glow, which contaminates the data. This is why the sunshield exists. It's a 5-layer, tennis court-sized barrier made from a material called kapton, designed to block heat from the sun, earth, and moon simultaneously. On the sunlit side of the shield, temperatures reach around 230 degrees Fahrenheit. On the cold side, where the telescope sits, temperatures drop to around minus 394 degrees Fahrenheit. The telescope operates in its own pocket of extreme cold, shielded from every source of heat that could ruin the measurements. Getting to that cold environment is part of why JWST orbits where it does. The telescope sits at the second Lagrange point, L2, about 1.5 million kilometers from Earth, in the direction away from the Sun. At L2, the telescope can always keep its sunshield pointed toward the Sun, Earth, and Moon at once. It never passes through Earth's shadow, which would cause temperature swings. It maintains a stable, cold, consistent thermal environment. That stability is not a luxury. For infrared astronomy at these wavelengths, it's a requirement. None of this was designed with Pluto in mind. The teams that spent decades building JWST were thinking about the epoch of reionization, about the formation of the first stars, about characterizing the atmospheres of exoplanets around other stars to look for signs of chemistry that might indicate biology. Those are enormous scientific questions, and JWST was built to answer them. Pluto was not a target anyone optimized the telescope for. And yet, a telescope designed to study the atmospheres of planets orbiting stars hundreds of light years away turns out to be very good at studying the atmosphere of a world about 5.5 light hours from Earth. A mirror designed to collect ancient light from the far edge of the observable universe turns out to gather enough signal from a tiny frozen dwarf planet to measure its thermal emission for the first time in history. A cold environment built to keep the telescope's own heat from contaminating data on distant galaxies turns out to be exactly cold enough to detect the faint infrared glow coming from Pluto's atmospheric haze. Most people, when they hear that JWST observed Pluto, picture a single instrument doing one kind of thing. That's not quite right. JWST carries 4 scientific instruments, each designed for a different purpose. Together they cover the full range of wavelengths the telescope was built to explore. They can image, they can take spectra, they can measure brightness variations over time. Each instrument had its own development team, its own engineering challenges, its own set of capabilities that no previous telescope could match. But one of those instruments, the one that would eventually give Pluto its scientific moment, was unlike anything that had ever been sent into space before. The instrument that finally cracked Pluto open is called MIRI, the mid-infrared instrument, and it operates in a range of the electromagnetic spectrum that, for studying solar system objects this distant, had essentially never been explored before. To understand why that matters, you need to understand what mid-infrared actually means. The electromagnetic spectrum is vast. Visible light, the narrow band of wavelengths human eyes can detect, sits between roughly 0.4 and 0.7 micrometers. Hubble operates mostly in that range. Near-infrared extends a little further, out to about 2.5 micrometers. New Horizons worked out there, but mid-infrared, the range from about 5 to 28 micrometers, is a completely different territory. It's not just a little further along the dial, it's a fundamentally different window onto the universe. And for cold, distant objects like Pluto, it's the window that actually matters. Here's what you need to understand about cold objects and infrared light. Everything with a temperature above absolute zero emits thermal radiation. The colder the object, the longer the wavelengths it emits. Pluto's surface sits at around minus 380 degrees Fahrenheit. That's roughly 40 degrees above absolute zero. At that temperature, the thermal emission peaks somewhere in the mid-infrared range, specifically in the wavelengths that MIRI was designed to detect. Optical telescopes can't see this. Near-infrared instruments can barely reach it. The thermal story of Pluto lives between 5 and 27 micrometers, and before MIRI, no instrument in space was sensitive enough to read that story. MIRI was built through a partnership between NASA and the European Space Agency. It took years of development, testing and engineering before it was ready. The instrument operates at a temperature of approximately minus 266 degrees Celsius. Think about that for a moment. Outer space, the vacuum between the stars, sits at roughly minus 270 degrees Celsius. MIRI has to be colder than most of outer space to function. The reason is simple but demanding. If the instrument itself is warm, it emits its own thermal radiation. That radiation contaminates the signal. To detect the incredibly faint thermal glow from a frozen world 3 billion miles away, MIRI had to be cooled to near absolute zero using an active cryocooler, a mechanical refrigeration system that keeps the detectors cold enough to prevent self-contamination. This is not a minor engineering detail. It's the reason the instrument can do what it does. 1 degree too warm and the data becomes noise. The spectral range MIRI covers, 4.9 to 27 micrometers, had been explored before for bright nearby objects, but for something as faint and distant as Pluto, no previous instrument had the sensitivity to detect anything useful. The signal from Pluto in this wavelength range is extraordinarily weak. Pulling it out of the background requires both a large collecting mirror and detectors with sensitivity that no previous mission could match. JWST's 6.5 meter mirror collects roughly 7 times more light than Hubble's 2.4 meter mirror. Combine that collecting power with MIRI's extraordinary detector sensitivity, and suddenly a signal that was previously undetectable becomes measurable. In May 2023, MIRI captured a high-quality mid-infrared spectrum of Pluto and its atmosphere, spanning that full range, 4.9 to 27 micrometers. That's not a photograph. That's a spectrum, which means MIRI measured how much thermal radiation Pluto was emitting at each individual wavelength across that entire range simultaneously. At specific wavelengths, 15, 18, 21 and 25 micrometers, MIRI also measured the thermal emissions separately from Pluto and from Charon. The data came back cleaner than the researchers expected. Spectral resolution matters here, and it's worth explaining what that means. When an instrument measures a spectrum, spectral resolution tells you how finely it can distinguish between neighboring wavelengths. A low-resolution spectrometer smears things together. Broad features that might actually be two distinct peaks get blurred into one. A high-resolution spectrometer can pull them apart. MIRI's spectral capabilities in this wavelength range represent a genuinely new level of detail. For comparison, New Horizons' infrared spectrometer had a maximum spectral resolution of about R equals 600. That number means it could distinguish between wavelengths separated by roughly 1 part in 600. JWST's instruments reach R equals 2700 in some configurations, more than 4 times finer. Chemical compounds have specific spectral fingerprints, narrow absorption and emission features at precise wavelengths. At low spectral resolution, those fingerprints blur into unrecognizable smudges. At MIRI's resolution, they become identifiable. The difference is the difference between recognizing a face and seeing a blur. Now, here's where timing becomes part of the story. In 2017, 4 years before JWST launched, a team of researchers published a study predicting that Pluto's atmospheric haze would produce a detectable thermal signature in mid-infrared wavelengths. The prediction was based on theoretical models of the haze's composition and physical structure. The haze particles, the models suggested, should absorb radiation and re-emit it thermally in a way that would show up clearly if you could measure Pluto in the right wavelength range with sufficient sensitivity. The prediction was specific, it was testable, and it was completely untestable with any instrument that existed in 2017. There was no telescope operating in space at that time that could detect Pluto's thermal emission at those wavelengths. The researchers wrote down what they expected to find, and then waited for an instrument that didn't exist yet. That instrument was MIRI. The gap between the prediction and the measurement was 8 years of patience, engineering, launch delays, commissioning, and finally, observations. 8 years from writing down the expected result to having data that could confirm or deny it. Scientists had predicted in 2017 that Pluto's atmospheric haze should be glowing in mid-infrared wavelengths, and MIRI was the first instrument ever built that could actually go out and test whether they were right. Even with the most sensitive telescope ever built pointed directly at Pluto, there was still a problem that had been waiting to derail these observations from the beginning. Here's what you need to understand about Pluto and Charon. They're not a planet and a distant moon. Charon orbits Pluto at a distance of only about 19,600 kilometers. That sounds like a significant gap. It is not. Our moon orbits Earth at roughly 384,000 kilometers. Charon is 20 times closer to Pluto than our moon is to us. These two objects are, in astronomical terms, practically on top of each other. And Charon is not small. It's about 1,200 kilometers across, roughly half the diameter of Pluto itself. In our solar system, there's no other case quite like it. No other planet or dwarf planet has a companion so large relative to its own size, orbiting so close. They're often described as a binary system rather than a planet-moon pair, and that description is accurate. They orbit a shared center of gravity that sits in empty space between them. Now think about what this means for a telescope trying to study Pluto's thermal emission from 6 trillion meters away. At that distance, the angular separation between Pluto and Charon, the gap between them as seen in the sky, is extremely small. Both objects appear nearly merged in telescope data. When an instrument detects infrared radiation coming from that region of the sky, it receives a combined signal: photons from Pluto's surface, photons from Charon's surface, photons from Pluto's atmospheric haze, all arriving at nearly the same position on the detector, all mixed together into a single reading. There's no clean edge where Pluto ends and Charon begins. For decades, this was the problem. One of the researchers on the JWST team described it directly. Basically, they couldn't know what part of the signal was due to Charon and what part was due to Pluto's haze. That's not a minor inconvenience. That's a fundamental ambiguity. You can't subtract Charon's contribution from the total if you don't know how much Charon is contributing. And you can't know that without being able to separate the signals in the first place. It's a circular problem, and it had no clean solution with any instrument that existed before JWST. Think about what this ambiguity actually prevented. Pluto's atmospheric haze was one of the biggest surprises of the New Horizons flyby. Researchers have theoretical models suggesting it should emit thermal radiation in the mid-infrared, but testing that prediction required measuring Pluto's mid-infrared spectrum accurately. That measurement required isolating Pluto's signal from Charon's, and that isolation required angular resolution and sensitivity that no instrument had ever demonstrated for objects this faint and this distant. Every path to confirming the haze thermal signature ran directly through the Charon problem. There was no way around it. Hubble couldn't solve it, even after the most careful data processing. Hubble's observations of the Pluto-Charon system suffered from stray light contamination, the signals of these two objects bleeding into each other in ways that image processing couldn't fully correct. Ground-based infrared observatories were worse. The combination of atmospheric interference, smaller mirror sizes, lower sensitivity meant that the combined Pluto-Charon signal was already barely detectable, let alone separable into two components. The Spitzer Space Telescope, that was designed for infrared astronomy, lacked the angular resolution to distinguish them at mid-infrared wavelengths. What JWST brought was two things simultaneously, and you needed both. The first was the size of its mirror. A 6.5-meter primary mirror gives JWST significantly better angular resolution than any of its predecessors. Angular resolution improves as the mirror gets larger. A larger aperture can distinguish objects that are closer together in the sky. At mid-infrared wavelengths, JWST's angular resolution was just sufficient to treat Pluto and Charon as separate sources, rather than a single blended signal. Not comfortably separate, not obviously separate, but measurably, usably separate, in a way that allowed researchers to build models of each object's individual contribution. The second was MIRI's sensitivity. Even with better angular resolution, separating these signals required detecting extraordinarily faint thermal emission from objects that are barely above absolute zero. If the instrument couldn't detect the signal clearly enough, any attempt to split it into two components would produce noise, not information. MIRI's sensitivity at 15, 18, 21, 25 micrometers was sufficient to capture the thermal emission from both objects with enough clarity that the separation was actually meaningful. But resolution and sensitivity alone didn't solve the problem. The separation also required careful orbital timing. Pluto and Charon orbit each other with a period of about 6.4 Earth days. As they orbit, their angular separation as seen from JWST changes slightly. Sometimes Charon is positioned more to one side, sometimes it appears more directly in front of or behind Pluto. By timing observations to catch Charon at a favorable orbital position, researchers could maximize the angular separation between the two objects. The signal separation more reliable. This wasn't brute force. It required planning the observations around Charon's orbital geometry, waiting for the right moments. Then combining those observations with sophisticated thermal models that accounted for the different surface properties of each body. The models themselves were built on everything previously known about Pluto and Charon, their sizes, their known surface compositions from New Horizons data, their distances from the Sun, their reflectivities. By constraining what Charon's thermal emission should look like based on all of that prior knowledge, researchers could estimate Charon's contribution to the combined signal and carefully subtract it. Pluto's individual thermal emission exposed for the first time. It was patient, precise, and deeply technical work, the kind of science that doesn't produce dramatic visuals but underpins everything that follows. Once the signals were separated, What researchers found in Pluto's thermal emission was something they had hoped to see but never quite believed they would. Direct proof of something that had only ever existed in climate models. In 2 papers published in the spring of 2025, an international team of researchers announced what they had found when JWST turned MIRI toward Pluto, and the results were the first of their kind in the entire history of astronomy. The team was led by researchers from CNRS, Paris Observatory, and the University of Reims Champagne-Ardenne. Their findings appeared in 2 journals. The first paper landed in Astronomy and Astrophysics in April 2025. The second came out in Nature Astronomy in June. Together, they represent something that had never existed before in planetary science, a measured, detailed thermal portrait of the Pluto-Charon system in the mid-infrared. Think about what that means for a moment. Every telescope ever pointed at Pluto across the entire history of observational astronomy had failed to capture this. Not because astronomers didn't try, not because the question wasn't worth asking. The mid-infrared thermal emission from Pluto and Charon had simply never been measured. The instruments didn't exist. And then, in May 2023, MIRI collected a high-quality spectrum of Pluto spanning wavelengths from 4.9 to 27 micrometers. That spectrum had never been obtained before, not even close. In addition to the spectrum, the team measured thermal emission from both Pluto and Charon at 4 specific wavelengths: 15, 18, 21, and 25 micrometers. These are mid-infrared wavelengths. They correspond to the heat glow that cold objects emit based on their temperature and composition. At these wavelengths, previous instruments were essentially blind when it came to Pluto. Too faint, too cold, too far. MIRI changed all of that. What the researchers were looking for in those measurements were light curves. A light curve, in this context, is a record of how the thermal emission from a source changes over time. As Pluto and Charon rotate, and they rotate together tidally locked, completing one full rotation every 6.4 Earth days, different parts of their surfaces come into and out of view. Different regions have different compositions. Some areas are covered in methane ice, others in water ice, some in dark, organic deposits. Each of these surface types has different thermal properties. They absorb and release heat at different rates. As those regions rotate into view, the total thermal emission from the system changes. As they rotate out of view, it changes again. By carefully tracking those changes at 4 separate infrared wavelengths, the researchers were able to extract information about the thermal character of these different surface regions, without ever resolving Pluto as more than a point of light. That's the key. JWST cannot photograph Pluto's surface in the mid-infrared. The planet is too small, too distant, but the thermal emission it produces still carries information, and that information changes as the planet rotates. The light curves capture that variation. Then the modeling begins. The data quality was better than the team had expected. That's worth saying plainly, because scientific observations often disappoint. Instruments hit their limits. Noise overwhelms signal. Results come back ambiguous. That's not what happened here. The measurements came through clearly. The thermal variations in the light curves were real and interpretable. The spectrum was high quality across its full range. For a target as faint and cold as Pluto, at a distance of roughly 40 times the Earth-Sun separation, this was not guaranteed. It was not even particularly expected to go this well. Here's what you need to understand about the phrase the researchers used to describe their findings. They wrote, "for the first time," not "for the first time with this level of precision," not "for the first time from this vantage point," for the first time, period. In all of human history, no instrument had ever measured the thermal emission from Pluto and Charon in the mid-infrared. These were not refinements of earlier results. They were the results. The baseline, the starting point from zero. That matters more than it might seem at first. When scientists build on previous work, they're filling in gaps, they're improving accuracy, they're extending known results to new conditions. But here, There was no previous work to build on. There were theoretical models, there were predictions, there were educated guesses based on what we knew about Pluto's composition and temperature. But there were no measurements. The 2025 papers didn't improve on something. They created something. The first observational record of Pluto's thermal emission at these wavelengths. A record that will serve as the foundation for every study that comes after it. Consider the span of time across which astronomers failed to obtain this data. Pluto was discovered in 1930. For 95 years, the mid-infrared thermal properties of this world were unknown. Ground-based telescopes couldn't do it. Spitzer couldn't do it. Hubble couldn't do it. New Horizons flew past Pluto at close range and never touched the mid-infrared. 95 years. Then MIRI collected a spectrum in 2023, and the measurements followed, and what had been completely unknown for nearly a century became measurable data in a journal. The light curves themselves told an immediate story. Thermal emission from both Pluto and Charon varied as they rotated. The variations were different at different wavelengths, which reflects the fact that different wavelengths are sensitive to different depths and compositions of the surface. Methane ice patches warm and cool differently than water ice patches. Dark organic material absorbs more heat and emits it differently still. The system of changes encoded in those light curves carries the fingerprints of the surface underneath. And the researchers began reading those fingerprints. At 15 micrometers and at 25 micrometers, the variations weren't identical. That told the team something. The signal at one wavelength reflected different surface conditions than the signal at another. Building a consistent model that explained all four wavelengths simultaneously required careful work, fitting the data against thermal models, constraining the possible values of thermal inertia and emissivity for different surface types, ruling out explanations that worked at one wavelength but failed at another. The spectrum added a different layer of information entirely. Where the light curves track changes over time, the spectrum tracks emission across wavelengths at once, a snapshot of how Pluto's entire infrared fingerprint looks at a given moment. Features appear in a spectrum when specific molecules absorb or emit radiation at characteristic wavelengths. The spectrum from 4.9 to 27 micrometers covered a range no instrument had ever probed for Pluto before. And within that spectrum, something appeared that researchers had been hoping to see for years. But the thermal light curves and the spectrum were only the beginning, because buried in that data was the confirmation of something scientists had been trying to prove for almost a decade. And it rewrote what we thought we knew about how Pluto works. The most significant discovery in the JWST Pluto data isn't something anyone saw. It's something they measured, something that had been predicted for 8 years and finally confirmed. Let's go back to 2017. A team of researchers published a paper. It was a modeling paper. Theoretical, predictive, the kind of work that doesn't make headlines. They ran simulations of Pluto's atmospheric haze. They looked at what the haze was made of, how dense it was, how high it reached, and they made a specific, testable claim. They said that Pluto's haze particles should be emitting thermal radiation at mid-infrared wavelengths, not reflecting light, emitting it, generating a detectable infrared glow of their own. The prediction was precise. It identified specific wavelength ranges. It gave expected brightness levels. It was the kind of scientific prediction that either gets confirmed or gets forgotten. There was just one problem. No instrument existed that could test it. Think about what that means. You do the math. You build the models. You publish the paper. And then you wait. Not for months, not for a year or two. You wait for an entirely new observatory to be designed, funded, built, launched, and commissioned. The instrument that could confirm or disprove your prediction didn't exist yet in 2017. It wouldn't exist until 2022. That's a long time to sit with a prediction you can't test. When MIRI finally captured Pluto's mid-infrared spectrum, the haze signature was there. Right where the model said it would be. The infrared glow from Pluto's atmospheric haze matched the predictions made 8 years earlier. in a paper written before JWST had even completed construction. That's not a coincidence. That's the scientific method working exactly the way it's supposed to work. Slowly, carefully, across years and instruments and iterations, arriving at something true. Now, here's what you need to understand about Pluto's haze. Before New Horizons arrived in 2015, most scientists expected Pluto's atmosphere to be relatively simple. A thin layer of nitrogen gas, maybe some haze particles low in the atmosphere, nothing spectacular. What New Horizons found was something else entirely. The haze extended more than 300 kilometers above the surface. 300 kilometers. Earth's atmosphere, the one that sustains all life on this planet, is effectively gone by about 100 kilometers up. Pluto's haze reaches 3 times higher than that. It was multi-layered, structured, far more complex and far more extensive than anyone had predicted before the flyby. And in images from New Horizons, it had a distinctive color, blue, a faint bluish tint visible against the blackness of space behind Pluto's limb. That blue color tells you something. It means the haze particles are scattering shorter wavelengths of light, blue light, more efficiently than longer wavelengths. The same reason Earth's sky is blue. The haze particles on Pluto are doing something similar. They're scattering sunlight. They're interacting with the electromagnetic spectrum in ways that leave a visible signature. But what are these particles? They're not simple compounds. Pluto's upper atmosphere contains nitrogen, methane, and carbon monoxide. Ultraviolet radiation from the sun, even at 40 times the Earth's sun distance, enough UV gets through, strikes those simple molecules and breaks them apart. The fragments recombine. They polymerize into larger, more complex structures. What you get are organic aerosols, complicated carbon-based molecules. The same class of chemistry that occurs on Titan, Saturn's largest moon, which has its own famous orange haze. On Pluto, the chemistry produces particles that float high in the atmosphere, scattering light, and as JWST has now confirmed, emitting thermal radiation. That last part is what matters. Scattering light is one thing. Emitting thermal radiation is something else entirely. It means the haze particles have a temperature. They absorb energy and they release it. They're thermally active. They participate in the energy budget of Pluto's atmosphere in a way that can be measured, tracked, and quantified. Before JWST, this was unknown. Not suspected, not partially measured. Unknown. The thermal behavior of Pluto's haze had never been observed. There were models, there were predictions, but observations? Nothing. The mid-infrared wavelengths where the haze emission was expected to appear, roughly 15 to 27 micrometers, had simply never been explored for Pluto. Not once, not by any instrument ever sent into space before JWST. When the spectrum came back, the signal was there, unmistakable. A thermal emission feature from the haze, sitting at the wavelengths the 2017 paper pointed to. The researchers describe it as the first direct observational evidence that Pluto's atmospheric haze has a significant thermal signature. First, direct evidence. That phrase matters. Not a detection inferred from other data, not a statistical hint buried in noise. A direct measurement of thermal emission from Pluto's haze. Here's why that's more than just a confirmation of an old prediction. Knowing that the haze emits thermal radiation tells you the haze is participating in Pluto's energy balance. Energy comes in from the sun. Some of it gets absorbed by the surface. Some gets absorbed by the atmosphere. Some gets radiated back out into space. The haze particles are part of that accounting. They absorb energy, they emit energy. The rate at which they do that, and at which wavelengths, changes how heat moves through Pluto's atmosphere. It changes the temperature structure. It changes which layers of the atmosphere are warmer or cooler than they would otherwise be. It influences the climate. That word, climate, might sound strange applied to something as cold as Pluto. Surface temperatures around minus 380 degrees Fahrenheit. An atmosphere so thin it would be considered a decent vacuum in a laboratory on Earth. And yet Pluto has a climate. It has a system by which energy is distributed and redistributed across the world and through the atmosphere. And what JWST confirmed is that the haze isn't just floating above that system, looking decorative. It's inside the system. It's part of the mechanism. The prediction made in 2017 wasn't just confirmed. It opened a door. Because now that scientists know the haze emits thermal radiation, they can measure how much. They can track how that emission changes over time. They can compare observations taken months or years apart and watch the haze evolve as Pluto moves through its long elliptical orbit around the Sun. A prediction that started as theory has become an observable, trackable feature of a real world. Detecting that signature wasn't just checking a box. It revealed that Pluto's atmospheric haze isn't passive scenery, but an active force shaping the climate of the entire world beneath it. What the haze thermal signature actually means for Pluto, what its implications are for how that world works, is where things get genuinely strange. Think about how climate works on other worlds. On Earth, the system is driven by greenhouse gases, carbon dioxide, water vapor, methane, that trap outgoing infrared radiation and warm the surface. Ocean currents redistribute heat from the equator toward the poles. The energy balance between incoming sunlight and outgoing radiation governs nearly everything. It's a complex system, but the basic machinery is familiar. We've studied it for over a century. On Mars, the climate story is different, but still grounded in things we recognize. Dust storms lift particles into the atmosphere and block sunlight. Carbon dioxide freezes out of the air in winter and deposits as frost at the poles, then sublimes back into the atmosphere in spring. The seasonal pressure of the entire Martian atmosphere rises and falls as carbon dioxide cycles between gas and ice. Strange compared to Earth, but the physics involved is the same kind of physics. On Titan, Saturn's enormous moon, you have a thick nitrogen atmosphere and a methane cycle that mirrors Earth's water cycle in a way that's almost eerie. Methane rain falls, methane rivers carve channels, methane lakes sit at the poles. The analogy to Earth's hydrological cycle is imperfect but recognizable. Pluto doesn't fit any of these frameworks, not even close. What the JWST data confirmed is that Pluto's climate, its temperature distribution, the way its atmosphere moves, which ices remain stable on the surface and which evaporate into the air, is apparently controlled by particles of organic haze suspended high in its atmosphere. Not greenhouse gases, not dust, not a liquid cycle. Haze. Tanguy Bertrand, the lead researcher from Paris Observatory, who led the analysis, described it plainly. This is unique in the solar system. That phrase sounds like scientific understatement, and it is. What it means is that among every planet, dwarf planet and moon with a substantial atmosphere that we've examined, nothing works quite like this. Here's how it functions. Pluto's haze particles, complex organic aerosols formed when ultraviolet radiation from the sun breaks apart simple molecules like methane and causes them to recombine into larger structures, float at altitudes extending more than 300 kilometers above the surface. These particles absorb incoming ultraviolet radiation. They also emit thermal radiation at mid-infrared wavelengths, which is exactly what JWST detected. That emission represents energy leaving the atmospheric system. Where that energy goes, and at what altitude it's released, determines how the atmosphere is structured from top to bottom. In most planetary atmospheres, temperature generally decreases with altitude up to a certain point. The surface is warmer, space is colder, and the atmosphere transitions between them. Pluto's haze disrupts this in ways that climate models are still working to fully capture. The haze absorbs energy at one altitude and radiates it from another. That changes the temperature gradient of the atmosphere, and the temperature gradient of the atmosphere drives everything else. Which direction air moves, where gases condense, how nitrogen and methane cycle between the surface and the sky. Now consider that Pluto's orbit is not a neat circle. It takes 248 years for Pluto to complete one orbit around the Sun, and that orbit is highly elliptical. At its closest approach, Pluto comes within about 30 astronomical units of the Sun. At its farthest, it stretches out to nearly 49 astronomical units. That's a meaningful difference in solar energy reaching the planet. And as the solar heating changes over those 248 years, the haze behaves differently. When Pluto is closer to the Sun, more ultraviolet radiation reaches its upper atmosphere, more haze particles form. The haze becomes denser and more energetically active. That changes how much thermal radiation it emits, which changes the temperature structure of the atmosphere below it, which changes the surface conditions. Some ices that were stable during the colder, more distant part of the orbit begin to sublimate. Nitrogen and methane shift from solid to gas. The atmosphere thickens slightly. When Pluto moves back toward the far end of its orbit, the process reverses. Less sunlight, less haze activity, cooling atmosphere, ice is refreezing and redistributing across the surface. The key point is that the haze sits in the middle of this entire feedback system. It isn't a passive layer of particles drifting through the air. It is the engine. Remove the haze, and Pluto's climate changes fundamentally. It is not decorative. It is not incidental. It is the primary mechanism by which this world regulates itself. That's what makes this discovery so significant. Scientists didn't just confirm that a haze exists. New Horizons had already shown us that in 2015, and the images were remarkable. What JWST confirmed, for the first time, is that the haze has a measurable thermal signature, which means it is actively participating in the energy budget of the planet. You can now quantify what the haze is doing. You can measure it. And measuring it is the first step toward understanding how much it changes across Pluto's long seasons, how it responds to variations in solar input, and what it means for the long-term stability of Pluto's atmosphere and surface ices. There's something worth pausing on here. We sent New Horizons across 3 billion miles of space. We got extraordinary photographs. We discovered mountains of water ice, vast nitrogen plains, geological features no one had predicted, and we still didn't understand the basic mechanism driving this world's climate. It took a telescope in orbit around Earth, staring at a point of light too small to resolve, measuring the faint glow of infrared radiation, to finally answer the question that the flyby raised but couldn't settle. The mechanism turned out to be haze, organic aerosols formed from broken methane molecules, rebuilt by ultraviolet light into complex structures, floating 300 kilometers above a frozen surface, absorbing and emitting radiation, driving seasons that last decades, reshaping which ices exist where across a 248-year cycle. A world of ice and frozen gas in the outer reaches of the solar system, with a climate controlled by particles of organic haze, it is, as far as anyone can tell, completely unique. One thing JWST cannot do from its position is take a detailed photograph of Pluto's surface. The dwarf planet is simply too small and too far away for its features to be resolved at mid-infrared wavelengths. That might seem like a serious limitation, and in one sense it is, but here's what most people don't realize. You don't need a photograph to read a surface. You need time, rotation, and the right instrument. MIRI provided all three. Here's how it works. Pluto and Charon are tidally locked to each other. They don't just orbit together, they keep the same faces pointed at each other permanently, rotating as a pair once every 6.4 Earth days. Think about that for a moment. One full rotation takes more than 6 days, as that slow rotation carries different surface regions into and out of JWST's line of sight. The total amount of thermal radiation coming from the system changes. Some regions run warmer, some run colder. Each one emits a slightly different amount of infrared energy, and MIRI is sensitive enough to detect those shifts in a single unresolved point of light. What you end up with is called a thermal light curve. It's a record of how the total heat flux from the Pluto-Charon system varies over time as the two bodies rotate. The light curve rises and falls in patterns. Those patterns aren't random. They're tied directly to which surface regions are facing JWST at any given moment. By comparing those patterns against detailed thermal models, researchers can work backward. They can figure out which types of terrain are responsible for which parts of the signal. The key quantity they're measuring is called thermal inertia. Thermal inertia describes how quickly a surface warms up or cools down when the amount of sunlight it receives changes. A surface with high thermal inertia, think dense rock or compacted ice, changes temperature slowly. It absorbs heat gradually and releases it gradually. A surface with low thermal inertia, loose dust, fresh snow, fluffy frost, responds much faster. It heats up quickly when the sun hits it, and cools down quickly when it doesn't. Different materials have different thermal inertias. This is important because Pluto's surface is not uniform. It's covered in a patchwork of different ices, dark organic deposits and mixed terrain. Each of those materials has its own thermal character. Nitrogen ice, which dominates the smooth, bright plains, behaves very differently from water ice, which forms the mountain ranges and the rougher terrain scattered across the planet. And both of those behave differently from the dark reddish material that covers large sections of Pluto's surface. Tombaugh Regio is the obvious starting point. That's the heart-shaped feature that New Horizons made famous. The smooth, bright left lobe filled with nitrogen ice plains. Nitrogen ice has a relatively low thermal inertia. It responds quickly to changes in solar heating. In the MIRI thermal light curves, Tombaugh Regio leaves a clear signature. When that region rotates into view, the thermal emission from the system shifts in a way that matches what models predict for a large expanse of fresh, loose nitrogen frost. Then there's Cthulhu Macula. This is the vast, dark region that stretches across Pluto's equatorial zone. Thousands of kilometers of terrain coated in tholins that are complex organic molecules that form when ultraviolet radiation hits simpler carbon-based compounds in the atmosphere and polymerizes them into larger, darker structures. Tholins are dark. They absorb more sunlight than bright ice. They also have their own thermal inertia profile, distinct from nitrogen or water ice. When Cthulhu Macula rotates into JWST's view, the thermal signal shifts in a different direction. The surface is warmer, the emission profile is different, and the light curve reflects that. Water ice regions add another layer. Water ice on Pluto is not the soft, loose kind you'd find in a snowbank. At Pluto's temperatures, water ice is essentially rock, rigid, dense, slow to change temperature. Its thermal inertia is high relative to nitrogen frost. When water ice terrain rotates into the measurement window, it leaves yet another distinct fingerprint in the light curve data. None of these regions can be seen directly by JWST at mid-infrared wavelengths. The telescope can't zoom in and point at Tombaugh Regio and measure it separately from Cthulhu Macula. Everything arrives as one combined signal from one unresolved point of light. The separation happens in the modeling. Researchers track how the combined signal changes through one full rotation, then another, then another. They fit thermal models to those changes. The models assign temperatures and thermal inertias to different surface fractions until the predicted light curve matches what MIRI actually measured. It's a kind of detective work that requires extraordinary patience. You're not reading the surface directly, you're reading the shadow it casts in time, watching how its thermal behavior shifts over days, using that behavior to reconstruct what must be there. Astronomers do something similar with exoplanet atmospheres. They can't photograph the atmosphere directly, but they can measure how the star's light changes as the planet passes in front of it and extract chemical information from those changes. The principle here is the same, applied to rotation rather than transit. What makes this approach genuinely powerful is that it doesn't require proximity. JWST is not at Pluto. It's sitting 1.5 million kilometers from Earth, and Pluto is roughly 6 trillion meters away. The thermal signal arriving at MIRI's detectors is almost incomprehensibly faint, and yet, by tracking how that faint signal shifts over 6-day rotation cycles, Scientists extracted meaningful information about the composition and texture of a surface they can't directly see. The thermal inertia maps painted a picture of a diverse, complicated surface, one where the composition of the ice and the darkness of the terrain left clear fingerprints in the data, if you knew how to read them. Beyond the thermal emission data, JWST's spectrometers were also reading the chemical fingerprints embedded in the light bouncing off Pluto and Charon, and some of what they found on Charon was unexpected. Every chemical compound absorbs and emits light at specific wavelengths. It's a kind of fingerprint. You shine infrared light on a surface, you measure which wavelengths get absorbed and which come back, and the pattern tells you what's there. This is spectroscopy. It's been a standard tool in astronomy for well over a century, but the quality of the spectrum you get depends entirely on the instrument doing the measuring. A low-resolution spectrum smears those fingerprints together. A high-resolution spectrum separates them cleanly. And what JWST brought to this problem was a level of spectral resolution that simply hadn't been pointed at Pluto and Charon before. JWST's NIA spec instrument achieves a spectral resolution of R equals 2700. That number describes how finely it can distinguish between neighbouring wavelengths. New Horizons carried a spectrometer called LISA. Its maximum spectral resolution was R equals 600. JWST's resolution is more than 4 times sharper. Think about what that means in practice. Features that blurred together in New Horizons data, overlapping absorption bands from different compounds, subtle signatures that got washed out, are now distinct and separable. Scientists were reading a document that had previously been printed at extremely low resolution. JWST handed them a cleaner copy of the same page. And on that cleaner page, on Charon specifically, 2 compounds showed up that no one had previously confirmed were there: carbon dioxide and hydrogen peroxide. Neither of these is exotic in a laboratory sense. Both are simple molecules, but finding them confirmed on the surface of Charon, separated clearly from everything else in the spectrum, raised immediate questions about how they got there and what they mean. Hydrogen peroxide first. This compound doesn't just appear on icy surfaces on its own. It forms through a very specific process. When water ice is struck by high-energy radiation, ultraviolet light from the sun, cosmic rays traveling through interstellar space, the energy breaks water molecules apart. The fragments recombine in different configurations. One of those configurations is hydrogen peroxide. It's a radiation product. Its presence is essentially a chemical record of exposure. Charon has been sitting in the outer solar system for billions of years, its surface bombarded continuously by whatever radiation the sun and the broader galaxy send its way. The hydrogen peroxide in Charon's surface ice is the accumulated signature of all of that. It's a clock of sorts. It tells you something about the bombardment history of that surface, how long it has been exposed, how deep the radiation processing has gone. Charon has no atmosphere to shield it. There's nothing to absorb incoming radiation before it hits the ice. Whatever the sun and deep space send, the surface takes directly. The fact that hydrogen peroxide is there is not surprising once you understand the mechanism. What's significant is that JWST confirmed it. Previous instruments had the right idea about what Charon's surface had probably experienced over billions of years. JWST now has direct chemical evidence. Carbon dioxide raises a different set of questions. Water ice on Charon was already well established. Ammonia-based compounds were known, but carbon dioxide ice sitting on the surface prompts the question of origin. Did it form there? Carbon dioxide can be produced through radiation chemistry. The same high-energy bombardment that creates hydrogen peroxide can also liberate oxygen from water molecules and carbon from organic compounds, allowing them to combine into carbon dioxide. That's one possibility. Another is that the carbon dioxide was delivered to Charon from elsewhere, perhaps from impacts by carbon-bearing objects over billions of years. A third possibility involves material from Pluto itself. Pluto's atmosphere sheds gas that Charon catches, and some of that captured material undergoes chemical transformation on Charon's surface and in its polar cold traps. It's not yet clear which of these processes dominates. What's clear is that carbon dioxide is there and that its presence needs to be explained. This is how compositional science at this scale works. You get the detection first. The explanation follows, through modelling and further observation and argument among researchers. JWST provided the detection. The explanation is ongoing. Meanwhile, Pluto's own spectrum from JWST added new detail to what was already known. Nitrogen ice, methane ice, and carbon monoxide ice had been identified on Pluto's surface before. New Horizons and earlier ground-based observations established those, but JWST's higher spectral resolution resolved features within those known absorption bands that hadn't been cleanly separated before. Different forms of methane ice, for example, behave differently depending on whether methane is sitting as a pure ice layer or mixed into nitrogen ice. The distinction matters for understanding how the surface chemistry is structured. At R equals 600, that distinction is difficult to make. At R equals 2700, it becomes clearer. There's something worth pausing on here. New Horizons flew past Pluto at a distance of about 12,500 kilometers. It was closer to Pluto than any instrument before or since. And yet, on the question of spectral detail, JWST, sitting nearly 8 billion kilometers away, extracted information that New Horizons couldn't. Proximity is not everything. In astronomy, it rarely is. The quality of your instrument and the wavelengths you can access often matter more than how close you are to the target. New Horizons gave us spatial detail, geological context, the first real images of Pluto's surface. JWST gave us spectral depth that proximity alone couldn't buy. That contrast isn't a criticism of New Horizons. It's a statement about how scientific tools are complementary. Different instruments reveal different truths. The flyby revealed what Pluto and Charon look like. JWST is revealing what they're made of and how they behave thermally. Both are necessary. Neither is sufficient alone. Finding hydrogen peroxide and carbon dioxide on Charon was not what anyone set out to discover. It was the kind of result that arrives as a consequence of finally having instruments sensitive enough to see what was always there. Pluto and Charon orbit each other as though dancing, locked face to face, never showing each other anything but the same hemisphere. And yet, over billions of years, they became completely different kinds of worlds. Think about what that actually means. Two objects, gravitationally bound from the beginning, rotating together, always facing each other across a gap of roughly 19,600 kilometers, formed most likely from the same catastrophic collision early in solar system history, a giant impact similar to the one that produced Earth's moon, that flung material into orbit around Pluto and eventually coalesced into Charon. Same origin, same neighborhood, same star heating them both at the same distance. And yet they are profoundly, almost completely different worlds. Pluto has an atmosphere. Charon does not. That single fact carries enormous consequences. Pluto's atmosphere is thin. The surface pressure is roughly 100,000 times less than Earth's, but it is active. Nitrogen, methane and carbon monoxide cycle between the surface and the sky. Ices sublimate when Pluto moves closer to the Sun in its elliptical orbit, feeding gas into the atmosphere. That gas freezes back out onto the surface when Pluto swings to its colder, more distant position. There is weather on Pluto. There is a climate cycle. There is haze. As the previous section established, that haze appears to control Pluto's temperature structure in ways scientists are only now beginning to measure and understand. Charon has none of that. Its gravity is lower than Pluto's, and whatever volatile gases it may have held early in its history were lost to space long ago. No nitrogen cycle, no methane haze, no atmospheric feedback loop. Charon sits exposed, Its water ice surface bombarded directly by ultraviolet radiation from the sun and by high-energy cosmic rays with nothing in between. That exposure has consequences of its own. Water ice under intense radiation chemistry changes. It reacts. Hydrogen gets knocked loose from water molecules. What remains can combine into compounds like hydrogen peroxide, which the JWST spectroscopic observations detected on Charon's surface. These are not compounds that arrived from somewhere else. They formed there, in place, as a record of billions of years of radiation exposure on an airless world. Charon's surface is, in a sense, a chemical diary written by cosmic rays. But here is where things get strange, and where the relationship between these two worlds becomes something more than just gravitational. Charon's polar regions are dark. They have a reddish tint, and for years, planetary scientists suspected they knew why, but confirming it required data that only JWST could provide. The leading explanation is that Pluto's escaping atmosphere is the source of that material. Pluto leaks. Its atmosphere sheds gas into space continuously, and some of that gas, methane in particular, drifts across the 19,600-kilometer gap and is captured by Charon's gravity and frozen onto its poles. Once there, it sits exposed to the same ultraviolet radiation and cosmic ray bombardment that dominates Charon's environment. And ultraviolet light hitting methane ice does not leave it alone. It breaks the methane apart. It drives chemical reactions. Those reactions produce complex organic molecules called tholins, the same kind of material responsible for the reddish coloration seen on many outer solar system objects. Those tholins are what make Charon's poles dark. Pluto's atmosphere is painting Charon, slowly, across geological timescales, but continuously and measurably. JWST's thermal observations gave scientists the ability to see this contrast directly. The regions on Charon covered in pure water ice have a distinct thermal signature. They heat and cool on a predictable schedule. Their thermal inertia reflects the properties of relatively clean ice. The dark polar deposits behave differently. They absorb more radiation. They have different emissivity values. Their thermal signature, when MIRI measured it at 15 and 18 and 21 micrometers, was measurably distinct from the water ice regions. This is not an interpretation. This is a measurement. Two different kinds of terrain on the same moon, producing two different thermal fingerprints, and the difference between them tells you something about what those terrains are made of, and where that material came fresh. What makes this so scientifically striking is that we are looking at an ongoing process. Pluto is still losing atmosphere. Charon is still capturing it. The polar deposits are still accumulating and evolving. JWST did not just reveal something that happened billions of years ago. It confirmed something that is happening now, in the current epoch of the solar system, between two worlds that have been gravitationally locked together almost since the beginning. Think about what that means for how we understand planetary systems. Two worlds form together. One retains enough mass to hold a volatile atmosphere. The other does not. The one that holds the atmosphere slowly loses it, and in losing it, transfers material across space to its companion. That companion is chemically altered by the material it receives. The darker, more radiation-processed surface absorbs heat differently. The two worlds, already diverging in their bulk properties, continue to diverge in their surface chemistry because of this continuous exchange. A closed gravitational system that is nonetheless chemically open, with material flowing from one body to the other indefinitely. This is not how most people think about moons. Moons are usually passive. They reflect light. They feel gravitational influence. They don't receive atmospheres from the worlds they orbit and chemically transform that material into new compounds that change their appearance and thermal behavior over billions of years. The idea that one world's escaping atmosphere could paint the polar ice caps of the world next door is the kind of thing that sounds like science fiction right up until you're looking at the thermal data that confirms it. One of the less publicized findings buried in the JWST Pluto data is also one of the more unsettling ones. Pluto is not frozen in place. Most people carry a mental image of Pluto as something static, a grey-white ball at the edge of everything, parked in the dark, changing on no timescale that matters. That image made sense when Pluto was just a faint point of light in a telescope. It made sense before New Horizons, before we knew about the nitrogen plains and the towering water ice mountains and the haze. But JWST has now pushed that image further toward obsolete. The thermal data coming back from MIRI shows something that contradicts the frozen, inert picture directly. Pluto's surface ices are moving, not fast, not in any way you could watch in real time, but they are moving, redistributing, sublimating off one region and depositing onto another. Driven by a climate cycle that runs for 248 years and answers to no human timescale whatsoever, here is what that actually means. Pluto carries three main volatile ices on its surface: nitrogen, methane, and carbon monoxide. The word volatile here is technical. It means these ices are unstable at Pluto's surface temperatures, in the sense that they can transition between solid and gas relatively easily by planetary standards. When sunlight reaches a region covered in nitrogen ice, some of that ice sublimates. It turns directly from solid to gas, rises into the atmosphere, travels, eventually refreezes somewhere else on the surface when conditions cool enough. This is the same basic process as Earth's water cycle, except the substance is nitrogen. The timescales are measured in Earth decades rather than Earth days. The world driving it is smaller than our moon. Pluto's rotation period is about 6.4 Earth days. That is one Pluto day. Over that single rotation, different surface regions move through sunlight and shadow. The thermal emission that MIRI measured varies as Pluto rotates. That is exactly what produced the light curves that researchers analyzed. But those diurnal changes, the day-to-day redistribution of heat across the surface, are only the smaller half of the story. The larger half is seasonal. Pluto's orbit around the Sun is highly elliptical. At its closest approach, it comes to about 30 astronomical units from the Sun. At its farthest, it reaches nearly 49. That is a difference of roughly 19 astronomical units, roughly 1.75 billion miles over the course of a single orbit. One orbit takes 248 Earth years. Think about that for a moment. Pluto's year is 248 of ours. The last time Pluto was where it is now in its orbit, humans were still decades away from building the first steam engine. The amount of solar energy reaching Pluto's surface at perihelion versus aphelion is not trivially different. As Pluto swings closer to the Sun, more energy reaches the surface. More ice sublimates. The atmosphere thickens. As it moves back out toward aphelion, the atmosphere collapses back onto the surface, refreezing. Nitrogen that was floating as gas during the warmer part of the orbit comes back down as frost. Pluto is currently about 35 astronomical units from the Sun, moving away from perihelion, that it reached back in 1989. The surface is slowly entering a cooling trend on seasonal timescales. The JWST data is showing evidence of this transition happening right now. The ice reserves are shifting. Scientists detected faint but measurable changes in the distribution of volatile ices that are consistent with a world entering a long, slow seasonal shift toward colder conditions. These are not dramatic changes, they are subtle signals in thermal data, requiring the kind of sensitivity that only MIRI can provide. But they are real, and they are happening on a timescale that no single human lifetime can fully witness. This is where JWST offers something that New Horizons fundamentally could not. New Horizons gave us one snapshot, an extraordinary snapshot, the most detailed close-up of Pluto ever taken, but still a single moment in time. July 2015, a few hours of close observation. Whatever changes were underway on Pluto's surface during that flyby, whatever subseasonal evolution was happening, New Horizons captured one frame of it and moved on. JWST is not moving on. It can return to Pluto repeatedly over months and years, measuring the same thermal signatures each time and comparing them. This turns a snapshot into a time-lapse. Scientists can now track exactly how Pluto's volatile ices evolve between observations, building a record of a climate system that operates far too slowly for any single mission to have captured on its own. There is something worth pausing on here. The sub-seasonal evolution that JWST can detect, changes occurring over years rather than over Pluto's full 248-year orbit, represents a level of geological and climate monitoring that was not possible before this telescope existed. Researchers can now ask whether changes currently underway on Pluto's surface were already in progress during the new Horizons Flyby. They can compare the 2015 baseline established by that spacecraft against years of JWST thermal observations and start to answer questions about how quickly Pluto's surface actually changes. That comparison between a spacecraft that flew past once and a telescope that keeps watching may turn out to produce some of the most scientifically valuable Pluto data we ever collect. What this reveals about Pluto's nature is hard to square with the frozen world image that most people still carry. Here is a world roughly 3.6 billion miles from the Sun, receiving less than 1,000th the solar energy that reaches Earth. Its surface temperature hovers around -380 degrees Fahrenheit. By any intuitive standard, it should be inert, fixed, a relic, and instead it has a nitrogen cycle, a methane cycle, a carbon monoxide cycle, all three operating simultaneously. Driven by a star so distant it appears as nothing more than an unusually bright point of light in Pluto's sky. The ice on its surface is not frozen forever. It is participating in a planetary system of redistribution that has been running quietly for billions of years. Pluto is a world in motion, slowly and on timescales longer than human civilization. But in motion, and JWST is now watching it happen. Pluto is not where astronomers usually look when they're thinking about the origins of life on Earth. But the chemistry of its atmosphere is turning out to be more relevant to that question than almost anyone anticipated. Here's what most people don't realize about early Earth. 4 billion years ago, our planet's atmosphere looked almost nothing like it does today. There was no free oxygen. There was no ozone layer. What existed instead was a thick blanket of nitrogen, carbon dioxide. Simple organic molecules, methane, hydrogen cyanide, trace hydrocarbons. Life had not yet had the opportunity to fill the sky with oxygen. The atmosphere was chemically reducing, hostile by modern standards, and yet somehow in that environment, life emerged. The specific chemistry of that early atmosphere matters enormously for understanding how that happened. And that is where Pluto becomes unexpectedly relevant. Pluto's atmosphere is dominated by nitrogen. The organic chemistry happening in that atmosphere, simple molecules being broken apart by ultraviolet radiation and reassembled into larger, more complex structures, produces exactly the kind of organic aerosol haze that some researchers believe may have existed in Earth's sky billions of years ago. Think about that for a moment. A frozen world at the edge of the solar system, at temperatures so low that nitrogen itself condenses onto the surface, maybe running a slow-motion version of chemistry that once ran in the air above a warm, wet, young Earth. The haze particles in Pluto's atmosphere are called tholins. That name covers a broad range of complex organic molecules. Reddish, sticky compounds formed when simple organic chemistry gets hit repeatedly with radiation. Tholins don't form easily in a laboratory. They require exactly the kind of nitrogen and hydrocarbon environment that Pluto provides. Scientists have been synthesizing tholins in labs for decades, trying to understand what early Earth's atmospheric chemistry might have produced. Pluto gives them a naturally occurring version to study, not in a vacuum chamber, in an actual planetary atmosphere, at scale, with real radiation inputs and real seasonal variation. The JWST mid-infrared data now adds something no lab experiment can replicate: a thermal record of how those particles behave, how they absorb and emit energy, how they respond to changing solar conditions over time. There's another world that fits into this picture. Titan, Saturn's largest moon, has been the primary natural laboratory for nitrogen hydrocarbon haze chemistry since the Voyager missions first revealed its thick orange atmosphere in the 1970s. Titan's haze is denser, its atmosphere is far thicker than Pluto's. The temperatures are different, the pressure is different, the chemistry produces similar results, complex organic aerosols in a nitrogen-dominated sky, but through a somewhat different pathway. For years, Titan stood more or less alone as the place to study this kind of chemistry in a planetary atmosphere. Pluto adds a second data point, and 2 data points, when you're trying to understand something as complicated as prebiotic atmospheric chemistry, are far more valuable than one. The thermal behavior of these hazes is the piece that JWST contributes directly. Previous instruments could detect haze particles by the way they scattered visible light. New Horizons gave us remarkable photographs of Pluto's haze backlit by the sun, layers of blue, extending hundreds of kilometers into the sky. But you cannot understand the energy budget of a haze system from photographs alone. The mid-infrared thermal signature that JWST detected tells scientists how much energy those particles are absorbing and re-emitting. That is the number that goes into climate models. That is the number that tells you whether the haze is warming or cooling the atmosphere around it, and by how much. Without that measurement, the climate models for Pluto were guesses. With it, they become something you can test and refine. The same principle applies to early Earth models. Researchers building simulations of the ancient terrestrial atmosphere have long debated whether organic hazes helped or hurt early life. On one hand, a thick organic haze would shield the surface from ultraviolet radiation, a potential advantage for early organisms lacking any other UV protection. On the other hand, the dense haze could reduce the amount of visible light reaching the surface. That would affect the energy available to early photosynthetic life. Where you land on that debate depends critically on the thermal properties of the haze, how efficiently it absorbs and re-emits radiation across different wavelengths. Pluto, with its measurable observable haze and its fresh JWST thermal data, offers a reference point for anchoring those models in something real rather than purely theoretical. None of this means Pluto is a perfect stand-in for early Earth. The temperatures are wildly different, the pressures are different. The solar flux reaching Pluto is a tiny fraction of what Earth receives. But in planetary science, analogues are rarely perfect. What matters is whether the underlying chemistry is similar enough to be informative, and the researchers involved in these JWST observations believe it is. The nitrogen chemistry, the hydrocarbon pathways, the formation of complex organic aerosols, all of it rhymes with what scientists think was happening in the atmosphere above an early lifeless Earth. The frozen edge of the solar system, it turns out, might hold some of the clearest evidence we have for understanding what our own world looked like when life was just beginning to figure itself out. None of this means we've figured Pluto out. What JWST gave us is a first look in a wavelength range that had never been explored before. That's genuinely significant. But a first look is not a complete picture. The list of things we still don't know about Pluto is long enough that it's worth being honest about. Start with the haze. We know now that Pluto's atmospheric haze emits a measurable thermal signature. That much is confirmed. What we don't know is the exact composition and structure of the particles producing that signature. We know they're organic aerosols. We know they form when ultraviolet radiation breaks down methane and other simple molecules and drives them toward more complex structures. But the precise makeup of those particles, the size distribution across different altitude layers, the specific chemical pathways that dominate the formation process, all of that remains uncertain. Climate models can reproduce the broad behavior of the haze, but models are only as good as the physical assumptions built into them. The JWST data constrained those models significantly. It didn't solve them. The mechanism by which Haze controls Pluto's climate is also still being worked out. The broad picture is confirmed. Haze particles absorb and emit radiation. This shapes the temperature structure of the atmosphere in ways that cascade down to the surface. But the specific feedback loops, the exact way Haze behavior changes as Pluto moves through different parts of its 248-year orbit, the interaction between haze formation rates and the availability of methane at different altitudes, these are open questions. They require more observations, more modelling, probably more time than any single set of JWST data can provide. Then there's Charon. The thermal data JWST returned placed significant constraints on Charon's surface properties. The discovery of carbon dioxide and hydrogen peroxide added real chemical detail, but the precise thermal history of Charon's dark polar deposits remains unclear. We think those regions are built from material that escaped Pluto's atmosphere and was chemically transformed by solar radiation after landing on Charon's poles. The broad process makes sense. The timeline, the rate of accumulation, the exact chemistry involved, none of that has been nailed down. Each answer tends to come with a set of follow-up questions. Here's what's encouraging though. JWST is not done. The telescope is expected to operate for at least 20 years, and Pluto is not going anywhere. Astronomers can observe Pluto repeatedly across different points in its orbit, building up a time series that no single observation campaign could produce on its own. Pluto's year is 248 Earth years long, which means JWST will never observe a full Plutonian season. But it can observe subseasonal changes, shifts in the thermal emission, changes in how the light curves look as Pluto rotates, variations in the Haze signature that might correspond to changes in solar heating as Pluto slowly moves along its orbit. That kind of longitudinal dataset is genuinely new. Before JWST, the best close-up snapshot of Pluto was a few hours of data from a spacecraft that sailed past and never came back. Now there's a telescope that can return to Pluto again and again, watching it change. The question of a dedicated spacecraft mission comes up whenever Pluto research is discussed. NASA has studied concepts for a Pluto orbiter, a spacecraft that would not just fly past but settle into orbit around the dwarf planet and spend years mapping its surface, sampling its atmosphere, tracking its seasons in real time. The science return would be extraordinary. An orbiter could resolve the surface features that JWST cannot, measure the atmospheric composition directly, watch the volatile ice cycle play out across multiple Plutonian years rather than inferring it from a single snapshot. The engineering challenges are significant. The travel time alone, even with a gravity assist from Jupiter, would be measured in decades. The cost would be enormous. No such mission is currently approved, or funded. Whether one eventually gets built depends on how Pluto's science develops over the next several years. Whether the community decides Pluto is a high enough priority to justify the investment. What has shifted is how Pluto fits into the larger picture of the outer solar system. The Kuiper Belt contains hundreds of thousands of icy objects. Some of them are large enough to be genuinely complex worlds in their own right. Eris, Makemake, Sedna. These are bodies that likely share some of Pluto's characteristics. JWST is beginning to observe them as well. Pluto serves as the reference point. It's the Kuiper Belt object we know best, even accounting for everything we don't know. The methods developed to study it thermally with MIRI can be applied to these other distant worlds. What we learn about how haze behaves on Pluto, what composition signals look like at mid-infrared wavelengths for nitrogen and methane ices, how to read a thermal light curve from a rotating icy body, all of that transfers. Pluto is not just a scientific target, it's a template. And this connects back to the opening premise. The reason any of this happened is that an instrument designed to look at the farthest galaxies in the observable universe turned out to be sensitive enough to detect a heat signature from a frozen world 40 times farther from the Sun than Earth. That was not an obvious outcome. The people who built JWST had exoplanets and early galaxies in mind, not Pluto. But the sensitivity required to see a planet forming around a distant star is related, mathematically, to the sensitivity required to detect thermal emission from a small, cold, distant body in our own solar system. JWST clears both thresholds, and the fact that it does means questions that seemed closed, or at least deferred until some future mission arrived at Pluto, turned out to be unanswerable right now, from a telescope parked 1.5 million kilometers from Earth. And that, maybe more than anything else, is what makes this particular discovery worth stopping to think about. That an instrument built to look at the edge of the observable universe turned around and told us something new about our own backyard, in wavelengths no telescope had ever looked at before. There's a way to think about what just happened with Pluto and JWST that makes it feel routine. One more telescope observation, one more paper in a journal, one more press release about something very cold and very far away. But step back from that framing for a moment. Really step back. Pluto is approximately 6 trillion meters from Earth. That number is almost meaningless on its own. Let's try to put it into some kind of shape. Light travels at 186,000 miles per second. Light can circle the entire Earth 7.5 times in 1 second, and light from Pluto takes more than 5 hours to reach us. 5 hours at that speed, that's how far away this world is. And from that distance, a telescope detected heat, not the glow of a bright star, not the infrared blaze of a galaxy. Heat from a frozen atmosphere surrounding a world smaller than our own moon. A world so cold its surface sits around minus 380 degrees Fahrenheit. A world that emits so little thermal radiation that for most of the history of modern astronomy, no instrument could distinguish its signal from the noise. Think about that for a moment. Every telescope ever built before JWST looked at Pluto and came back with incomplete answers. Hubble could resolve it as a blurry disk. It could map rough patches of light and dark across the surface. But the mid-infrared range, the wavelengths where Pluto's thermal story actually lives, remained completely blank. Not uncertain, not approximate, blank, unknown, a gap in human knowledge that existed simply because the instrument capable of filling it hadn't been built yet. And then MIRI was built, and pointed at Pluto, and the haze glowed exactly where the models said it would. Here's what most people don't realize about that. The prediction was made in 2017. Scientists published a specific, testable claim. Pluto's atmospheric haze should emit detectable thermal radiation at mid-infrared wavelengths. They wrote it down, they committed to it, and then they waited. Not because they were patient by nature, but because they had no choice. The instrument didn't exist. It was still being designed and assembled and launched and cooled down and commissioned. 8 years passed between the prediction and the confirmation. 8 years of not knowing whether they were right. When the JWST data came back, the signal was there, exactly where it was supposed to be. That's not a small thing. That's the scientific method working at its most fundamental level, across a span of years and an expanse of space that challenges every attempt at comprehension. Pluto was written off at every stage of this process. Too small, too far, too cold, too close to Charon. Every objection was legitimate. Every limitation was real. None of it was wrong. The physics was correct. The obstacles were genuine. And JWST cleared them anyway, not by making the physics easier, but by being precise enough and sensitive enough and cold enough to work within physics that no previous instrument could survive. The photons that made this discovery possible left Pluto's atmosphere and traveled outward across billions of miles of empty space. They traveled for hours. They crossed the distance between our Sun and Pluto's position, 40 times the Earth-Sun distance, and then they kept going. They arrived at a mirror made of 18 gold-plated beryllium segments, each one polished to tolerances measured in nanometers. They passed through an instrument cooled to temperatures colder than outer space. They were counted, recorded, processed, and turned into a spectrum. And that spectrum contained the first thermal emission measurement from Pluto's haze in the history of human astronomy. Not the most precise measurement, not the most detailed, the first. Before May 2023, that measurement did not exist. No one had ever made it. Every scientist who had ever studied Pluto, every paper ever written about its atmosphere, every model ever constructed of its climate, all of it was built without that measurement. Now it exists. Now we know the haze glows. Now we know it controls the climate. Now we know something about how Pluto's surface ices move and cycle and redistribute across a 248-year orbit. We know things about Charon's polar chemistry that no one had confirmed before. All of it came from a telescope that, by the physics of the problem, had no business seeing any of it. That's worth sitting with. The edge of the solar system, a frozen world, a haze of organic particles floating 300 kilometers above a surface of nitrogen ice, and a mirror in space that caught the heat and sent back the proof. Thank you for spending this time out at the edge of the solar system, and remember, the next time someone tells you something is impossible to see, the universe has a way of waiting for better instruments.